Okay, we're going to continue on here. We're going to continue on chapter 11, hopefully wrap it up and roll into 12 officially. Then we will roll out of here, I think. Yeah. So chapter 11, we started talking about alkenes, alkynes. Oh my, here we go. Alkenes, which again have our carbon-carbon double bond, our alkynes, which is our carbon-carbon triple bond as the functional group. We got into obviously naming them, and as we talked about, kind of like normal naming, except here when we do get to the numbering of the longest carbon chain, we do want to give the double bond or triple bond the priority in terms of numbering. So in that case, whichever way is sort of shortest for your double bond or triple bond in terms of the numbering. And as I think it was a question last time, it is where the double bond or triple bond sort of starts is the number that we need to give. And once you figure that out, everybody else that may be attached or groups would be numbered accordingly as depending on which way that you do. That's a little bit different, obviously, than alkanes, where we sort of give the priority to the groups that are there, and we want to give the groups a smaller number. But here we do want to go with the double bond or triple bond. Now, you really have to give the number for the location, double bond or triple bond, when it starts to make a difference in a sense of there's more than one place as to where you could put it. So usually around 4 carbons or so, that's about where you got to kind of insert the number. Obviously, if you have 2 carbons, there's only one place you could put that bond, right? That double bond or triple bond is going to be between the 2 carbons. So you really don't need it. If it is a tie in terms of which way, it doesn't matter which way you go for the double bond or triple bond. Then what you would want to kind of do is default to the next important thing, which would be the groups. Then you would want to go whichever way would perhaps give the groups the smaller set of numbers. So if you do come up with a tie, that's sort of the next thing that you should sort of look at is the groups that are attached to give them the smaller number. But if there is not a tie, then obviously double bond or triple bond takes priority. We could also have a double bond or really even a triple bond in a cyclo sort of structure, and it's named pretty much like cycloalkanes, except we put the ene if it's a double bond. We do not need to give the location of the double bond in a cycloalkene, like if we had this guy here. That would just be cyclopentene. Again, there's no other groups attached, so you don't have to give the location of where the double bond is located. It's assumed that that guy would be bond number 1. I'd say double bond number 1, but that doesn't sound right. But that would just be bond number 1. If we do have a group that finds its way onto the ring, then we do need to give the number of the group. And remember, one of the things that you should remember when you do have this type of situation is we still want to give, in this case, the double bond the smallest number, which means we do want to start at the double bond. But one of the rules is you have to actually number through the double bond to get to that group. So again, you could not just go directly away from the double bond and number in that fashion. Your option would be to start with 1 there and go around that way. Or obviously your other option would be start the other side of the double bond and come around obviously clockwise, and clockwise obviously gives that group there a smaller number. So that'll be something like 3-methyl cyclopentene in that case, based on what we just kind of put there. So a little 3-methyl cyclopentene. Yeah. We talked about as well cis and trans isomers, and again, cis means the same side of the double bond we're talking about here. Trans is opposite sides of the double bond. And remember that in order to sort of have the ability for something to be a cis or trans isomer, you really want to look at the double bonded carbon, and each individual carbon needs to have different groups attached. So they can't have the same group on the same carbon in the double bond. If they do, then you can't have cis or trans. Kind of eliminates the possibility of that. So that's the first thing you want to kind of look at to make sure that when you look at the double bonded carbons, each carbon individually has two different groups attached. When we're doing cis and trans, you could also look at hydrogen as sort of a group off of that as well. And the other thing that they also need is a group that is shared between the two opposite carbons, like we have here in this case here, and they would obviously be on the same side in this example. And this again would be a cis isomer. We do add the cis or trans to kind of the beginning of the name. And, this would be cis, whatever it may be here. Remember, though, that if you are asked to sort of name something that is drawn in sort of a cis or trans sort of way, you want to focus still on the longest carbon chain. So sometimes people, when they're drawn sort of in the cis or trans arrangement, they just always kind of look at the double bond because that's what they're focusing on. And like I said, maybe laying time every name ends up being ethene because there's two carbons right there directly in the middle, and they start naming all the rest of the stuff as groups. So I think maybe we had something perhaps like down like this. Let's gotta go this way. And we'll do an H and like an H. So remember that if we were going to name this, we would want to run the longest carbon chain, which pretty much takes up everybody in this particular case. And again, that obviously would be more like a butene than an ethene. So sometimes people get really hyper focused on just the double bonds there when they're going to name it. We also talked about drawing sort of a cis or trans if you needed to do so. My recommendation would be just to draw it straight without the cis or trans. I would then isolate your double bond and figure out what your four groups are going to be, and then redraw it, sort of arranging the groups in the proper sort of cis or trans arrangement. That's really a good way to do that. We talked about reactions that these guys undergo, and they do undergo addition reactions, which pretty much means that they all pretty much run the same way. At the start of the reaction, and by the way, it is only where the carbon-carbon double bond is where all this is going to happen. Doesn't matter what else you have drawn with those double bond. That is really the point where everything sort of occurs. We're going to add something to it, and it could be two things that are the same, could be two things that are different. And as we talked about last time, we really, as it sits, for example, in this here, there's no more room really to put anything on those carbons. So what always happens in the situation is we just got to turn our double bond into a single bond, and nothing else changes in terms of your molecule other than you do that. And now what that does is it frees up room for these guys to add in. And again, they do add in one at a time and one to each of the carbons that are there. And you will end up with something like this. So we talked about adding something like hydrogen, which is referred to as a hydrogenation reaction. It basically turns our double bonds into single bonds. So we go from alkenes to alkanes. We also could do something like water, or anything else with hydrogen, like HBr, HCl maybe as well. We could add something like that. And by the way, with hydrogen, we could also do something similar with bromine, chlorine as well. Those are what are referred to, as I talked about last time, sometimes referred to as symmetrical addition reactions, because frankly, you're adding two of the same things. So it doesn't really matter where you put it. Here, we're adding two different things. Water is always sort of thought of as H and OH is sort of how it gets added. So we add an H and an OH, one to each of the carbons. Here we would add like an H and a Br would be added here. And again, now if the original carbon-carbon double bond, as we talked about, everybody has the same number of hydrogens. In the situation where you're adding hydrogen to something else, it really doesn't matter which carbon you put the hydrogen on or which carbon you put the other guy on. If they do have different numbers of hydrogens, which I terribly tried to draw one time last time, and it didn't work out so well, but we'll maybe just do a simpler one like that. If we have something like this where we have some different numbers of hydrogens sort of happening, when we add something with like HOH, HBr, the H will always end up at the carbon that had the most hydrogens to begin with. That's known as I'm gonna try to spell Makovnikov-ish. I feel like I butchered that pretty badly there. But so that's basically in this case, we would still just break the double bond. And I was gonna look that up and spell that correctly, probably. We got an H going on to that guy, and then our OH would go on, for example, to that side. And what that will do, as we talked about last time, is it will give you really the what's referred to as the major product, and the minor product would be just the opposite, basically done. In most cases, when you draw it, you do want to draw sort of the major product. This obviously gives us, as I diverted last time, into an alcohol, right? And the alcohol is that OH group that goes on here. So when we add water to an alkene, we get an alcohol. That's what is sometimes also referred to as a hydration reaction, because we're adding water to do so, and it will produce basically a alcohol. Any questions on any of that stuff there? Like I got up to there right after there. I'm not so sure I got the rest of the spelling right there. I think. All right. So here's our hydrogenation. As we also talked about last time, oftentimes a lot of these are sort of catalyst driven. So you'll sometimes see things on top of the arrow, like platinum, nickel, palladium. And again, they're just catalysts to allow this reaction to occur a lot faster. They really won't have any sort of impact on what you're drawing or what you need to draw in terms of your product. So really for our purposes in this class, you could kind of ignore that fact and don't really worry about it. It's really, in our case, just the hydrogen. And obviously in this particular case, it's going to be happening. Did we do this one? I don't remember if we did or not. I feel like we stopped maybe here on this one. So why don't we do this one here? Why don't you draw the equation and what's happening here for the hydrogenation of 1-butene? Did we? I feel like almost at the end we maybe did it. Yeah. Okay. Then maybe we did this one. Then we'll go to the next one. How's that? I like it. All right. So I think we were also talking about towards the end here, hydrogenation of oils. And again, as I mentioned, I think at the end there as well, this is what is sometimes referred to as being partially hydrogenated. They add hydrogens to it. It actually increases the melting point because it allows really the carbon chains to sit much nicer with each other. We'll talk a little bit about this when we talk about fatty acids in the lipids chapter towards the end. But what happens when you have double bonds in this part of the molecule is it actually creates kinks in the chain. So instead of things sitting really nicely with each other, they kind of kink out all these things. And you end up getting not great interaction sort of happening, as opposed to when you kind of turn that thing into a single bond. This guy stays pretty straight, which means if you have another guy coming in there, they're going to be able to kind of line up really nicely with each other. And that really does sort of change sort of the properties of those type of things. Let's try these, which I don't think we did. So let's try these guys here. And let's also do. Okay, so let's take a look and see. So remember that when you are going to draw these things, sometimes people freak out over the drawing part of it because I'm not really sure what I should draw. And again, sometimes people do kind of weird things and draw things weirdly and stuff like that. So trust me when I say in this class, pretty much what you start with is almost what you end with. Just small little changes is what you should make. So again, you pretty much have the structure that you need. So I just redrew it up here so we could kind of isolate the double bond. And the reason we're going to isolate this double bond is, again, that's pretty much where everything's going to happen. And that's the thing that we need to turn into a single bond. So really, you can pretty much just jam right through it and copy exactly what's over there. And again, all you essentially got to do is turn that double bond into a single bond. And again, nothing else changes. So don't get fancy with it or funky with it or anything like that. Don't turn it into a ring or anything of that nature. And then at that point, we now have room for, in this case, our hydrogens. And again, they go one to each of the carbons. So we would just slap a hydrogen there on each of those. And then we would be in business at that point. Yeah. Any questions on that one there?
Say that if you left it CH and just remove the double bond and added a hydrogen.
Yeah, so I drew a little combo of condensed and expanded here just to see the part that changes. But you could have, if you're asking, could you just done this? You obviously need to add the hydrogens to each of those and to H2s, and that'd be fine. Yeah, that'll just be the condensed structure there. Other questions on that there? All right, same thing here. This is a cyclo structure with a double bond. So once again, that is the only thing that's going to change. And by the way, it's not going to open up and do anything weird like that. It's going to stay closed. And we're just going to do the exact same thing here, which is pretty much just copy what we got going on there. Except in this case, we're just going to turn it into a single bond, which means don't draw the double bond, right? By doing that, and by the way, to start with, there is one hydrogen at each of those spots. Now that we got rid of the double bond, we make room for the hydrogens that we want to add here. And again, we would add, just to show it perhaps, we'll just show that we put the hydrogens on, even though you don't really need to. If you drew this the picture originally, it implies that there's two hydrogens there and that you put kind of the hydrogens on there as well. Other questions on that? So again, in this particular case, because it is sort of line structure, you actually could just draw it like that, and it would imply that they would have the two hydrogens sort of there. Any questions on that there? All right, top one, we're adding water, and water here is going to be our H and OH, and we're going to again still only focus in on our double bond, which is right here. And nothing else is going to change. So we can, again, just copy it directly like it is. I'm going to go with a, where am I going to go with that? I can go up top. I can go over here. CH3, C, we're going to make that into a single bond. We will still have the CH3 on the bottom. We will still have the hydrogen up there. We'll have our CH2 and our CH3. So frankly, I'm just copying what's there. Now I have room, and I'm going to add an H and an OH. And in this case, dare I say, third time's a charm, maybe we're going to follow Markovnikov's rule here, which is the hydrogen should end up on the one that had the most hydrogen to begin with. And in this particular case, it would be our carbon on the right here, right? Had more hydrogens. So that is where, I'll put a different color so we can see it. That is where the hydrogen should add. That means my OH should be over here as well. Yeah. And again, that would give us our major product in this case. Any questions on that? I think I did not bad. I think I forgot the V there originally, but what you can do. Any questions on that there? So you do need to be able to obviously draw the products here if you're just given the front part, and draw correctly, you know, everybody coming on correctly. All right, let's see. We talked about our hydration reactions again, creating our alcohols. So why don't you do this one as well? Why not? Okay, so let's take a look at it. And again, if it's helpful to you, I'm just going to kind of draw out everything around the double bond, because I know that's kind of where everything's going to happen. So it might be helpful just to kind of visualize what's happening. If you want to draw out all the other hydrogens, you can as well. So we'll have that going on. We've got a little double bond action, we've got carbon and a couple of hydrogens. And here again, we're going to add our water. So once again, we're going to focus in on our carbon-carbon double bond. And once again, that is going to be really the only thing that's going to change here. And because we're adding hydrogen and something else, sort of an unsymmetrical addition here, we do want to look at the carbon-carbon double bond, and they actually do have different numbers of hydrogens. So we know that in this particular case, the one that had the most hydrogens to begin with is over here. And that is where our hydrogen should end up when it's all said and done. But before we do that, we could get to the drawing part, which again, I'm just going to copy. So CH3, CH2, carbon, hydrogen, single bonded, carbon, hydrogen, hydrogen. So in a matter of 5 seconds, I have pretty much 99% of the molecule drawn for me by just copying what was there to begin with. And now we're just going to put everybody in the right spot here. So we'll lay up a hydrogen there, and we'll lay up an OH right there. And we'll end up with something like this as well. Now, if you were going to go full condensed, obviously you would bring the hydrogens back in and leave the OH as the only thing kind of hanging out there attached. Any questions?
So the OH goes where it's the most carbon.
The hydrogen should go to the hydrogen should go to the carbon that started with the most hydrogen to begin with. So we're looking over here. So this carbon has 2 hydrogens. And this carbon originally in the double bond has 1. So the hydrogen should end up at the carbon that had the most hydrogens to start with. So that's the guy on the right.
For the test, is that okay, or do you want us to put it in the condensed version where the H's?
I'd be fine if you drew it like that, to be honest with you. I'm okay with it. But if you want to put it into condensed, or if you want to expand out all the hydrogens, you can. As long as the instructions doesn't say specifically, like, draw it in a condensed or something like that. So again, I'm just kind of drawing out the double bond area so you can kind of see where everybody ends up. But again, if you were going to just kind of turn it into a condensed, it would look something like this. And then you'll have your OH hanging off of there, basically. So it looks something like that. Other questions? So hydrogen to the carbon, most hydrogens. Other guy to the opposite. Yeah. Yeah. Yeah, so I would expand it, or you don't have to expand it. It's up to you, whatever you want to do. But just so we're clear, when we're talking about most hydrogens, we're talking about directly attached to that carbon. So just directly attached to that carbon, not right straight bonded to that carbon is what we're talking about. So even though, there's a bunch of hydrogens hanging out over here on the left, we're not talking about those hydrogens or anything like that. We're talking about the ones that are directly attached to the 2 carbons that make up the double bond. The one on each side. Other questions? Okay. All right. So let's then talk about another class of organic compounds, which are aromatic compounds. Aromatic compounds have what we like to call in organic chemistry a benzene ring. And this is a benzene ring. It's a 6-carbon ring with 3 double bonds. You can also draw what is referred to as a resonance structure, like we talked about, I think, in Lewis structures, where the double bonds head in the opposite sort of 3 guys. That also means, as you can see here, these are all hydrogens. There's 1 hydrogen at each of those carbons because of those double bonds. I would say for simplicity in books like ours, sometimes they will draw the benzene ring, which is a circle kind of in the middle. And the circle indicates that those double bond electrons are delocalized, they're moving around, which is basically what the resonance structure means. They can be on 1 carbon or the other. So sometimes you'll just see it drawn with kind of like a circle in the middle. It still has the 3 double bonds happening there. It's just sort of a shorthand that's sometimes used for the benzene ring. So this is not, by the way, this is not the same as this, because that is what? That is cyclohexane, right? So that's a cycloalkane. That is not a benzene ring, by the way. If you have that right there, what I just drew is cyclohexene, also not a benzene ring. For it to be a benzene ring, you need the 3 double bonds. Was maybe the question was asked. Yeah. So for it to be a benzene ring, it has to have those 3 double bonds in it, and it will look either with the 3 double bonds drawn out, or probably a lot of times in our book and places here, you'll probably see it more drawn again with that little circle sort of in the middle, and those represent benzene rings. So those are different things, even though they're kind of look the same. And they're different because, again, because of the presence of the 3 double bonds means that the benzene ring only has, for example, 6 hydrogens, and something like this has actually 2 hydrogens at each of the spots all the way around. And obviously this guy has 2 hydrogens at each spot, except for where the double bond is, he's got 1 hydrogen happening there as well. So they have different numbers of carbons and hydrogens, and they are different things. So one of the problems that sometimes happens is people see that ring type structure, and it's always now going to be like a benzene ring always. So it's got to have those double bonds in there, 3 of them, or it's got to have that circle for it to be a benzene ring, and that's what makes it sort of an aromatic compound. Question on that there, yeah.
Does it have to always be C6H6, or could it be like CnH10?
No, so benzene for the most part is that right there. So it's that arrangement of carbons and hydrogens together, if that's your question. That is basically.
All aromatic compounds are C6H6?
Yeah, and they have other things attached to them, but the basis of what it is, almost like the longest carbon chain or the basis of what it is, it has at least that benzene ring in it and stuff like that. Now, sometimes, as we will see, sometimes the hydrogens are substituted out for something else, like something else that we've seen, and it will have a different name or something like that. But the basis of sort of the biggest part of it is that foundation of kind of the 6 carbons arranged with that with the double bonds happening. So I won't say it will always necessarily have the 6 hydrogens because they can substitute out for some other things, but it definitely will have the 6 carbons and basically the 6 hydrogens if something's not substituted out will be in there. So looking at that, these are all, again, versions of what a benzene ring looks like. And like I said, a lot of times we'll kind of see it like that with kind of the circle drawn in there. And again, it still has the 3 double bonds that are happening in the carbon part of it. Now, when we name these guys, we can draw it. And there are certain aromatic compounds that are benzene containing that have some historical type names that people still use today. So for example, this benzene ring that basically has a methyl group on it, that is what is known as toluene. So toluene is basically a benzene ring that has a methyl group on it. You could also just kind of name it like you might think, which is you just name the group and put benzene at the end of it. So that would also be known as methylbenzene because it has a methyl group and it's a benzene ring. So sometimes it's referred to as methylbenzene as well. And this would be it in line structure, right? Our lonely line with nothing at the end of it is a methyl group. So that would be its version of it. If you have a benzene ring that has a nitrogen containing group like an NH2, these are amines, as we'll talk about in a later chapter, another organic type of group. And that is what's sometimes historically referred to as aniline. So if you see like a benzene ring that's got like a nitrogen, 1 hydrogen, 2 hydrogens, maybe some other things on there, that's going to be a form of aniline. If you have a benzene ring with an OH group, that is what is known as a phenol. Sort of like an alcohol type of situation happening here. And again, those are 3 very common names that are still sort of used and the sort of historical type of names that are still used today. Now, if we look at this here, we can name this as a couple of things. We have a chlorine group here and a benzene ring. So again, we just kind of name the group and put benzene at the end of it. So that would be a chloral benzene. Here we do not need to give the location because it only has one thing on the ring. So wherever that chlorine is located is carbon number 1 in this particular case. Now we do have 2 things on the ring here. And that is now going to be 1,2-dichloral benzene. Dichloral because there's 2 chlorines in the compound, just like normal. We use the little prefix. Location 1 and 2 is the simplest way. The nice thing about a benzene ring is there's 3 double bonds, which means you could go any way in terms of numbering. You should always be going probably across a double bond when you're numbering it and stuff like that. By the way, the 1,2 positioning on a benzene ring also has a name that is sometimes referred to as the ortho positioning, or just O for ortho. So sometimes people will use ortho instead of the numbering and call this ortho or O. As it moved, there it is. Call it ortho or O dichloral benzene. And again, if you see something like ortho or O, it represents that you have groups at carbons number 1 and number 2 on the benzene ring. And that's specifically used for benzene rings that have a couple of things attached to it, that sort of ortho arrangement. If our CLs move, we now kind of move from 1, 2, and 3, and that is 1,3-dichloromethane. 1 and 3 positioning on the benzene ring is known as meta, or M. And again, sometimes people will refer to this as M-dichloral benzene. And when you see the M or the meta, it's basically telling you their chlorines are on 1 and 3, as opposed to over here where it's ortho, where the chlorines would be on 1 and 2. So those type of numbering or names are also used a lot. And here, if we kind of move our chlorine opposites of each other, it will end up at 1 and 4 on the benzene ring. And as you could probably imagine by now, that also has a name which is known as para, or P. And again, sometimes people will call that P-dichlorobenzene. And again, instead of using the numbering, if you see para or P, it means that they are 1 and 4 of each other on the ring, basically opposite locations of each other on the ring. So ortho 1-2 positioning, again, specifically for just a benzene ring. If you have something on the 1 and 2 positioning, that is the ortho positioning. Meta is 1 and 3 on the benzene ring if you have groups there. And para is 1 and 4 on the benzene ring. Any questions on that? No. So in order to use those sort of prefixes, it has to be a benzene ring, and obviously you need 2 groups attached on it. So here, if we look at some of these names, we have 3-bromoaniline. So if we take this part here, that is our benzene ring with a nitrogen group on it, which is where the aniline part of the name comes from. And since that's going to be our priority here, that's going to be carbon 1, 2, and 3. And that is where our bromine is attached. So that's going to be 3-bromoaniline. Here we have a phenol ring happening right there. So that is the phenol part of it. And now, because that has to be carbon number 1, if I went clockwise in this case, my groups are going to have larger numbers. So in this case, I can go counterclockwise, again, because there's 3 double bonds. So you will go through the double bonds doing it that way. That's going to give me a 2 for the chlorine and a 4 for the bromine. And again, we still go alphabetical order, right? So that is how we get our 4-bromol, 2-chloral, and again, phenol at the end of it, as that's sort of that one, that historical type names. And lastly here, right about there, that is our toluene that we see. And that means that we have a bromine group and another bromine group, which is 2 bromo groups. And that is where our dibromo comes from. We also have a chloral group as well. And obviously we're going to number, in this case, I don't think it matters which way you go. You can go right or left, because carbon number 1 has to be where that methyl group is. So in this case, I think you're going to hit the same numbering no matter which way you go. But we'll end up with a 2 and 6 for our bromine groups and a 4 for our chloral groups. Any questions on that there? So sometimes these are hard to see, especially if there's a lot of other stuff in there to kind of see those kind of historical groups. So you just want to kind of be on the lookout for a benzene ring. If there's an OH there, then it's probably going to be phenol. If there's a CH3, it's going to be toluene. Or again, a nitrogen containing group would be aniline in that case. Any questions on that there? All right, so let's take a look at these. Take a moment and decide for the first one and the second one, what might be the correct name here. And we definitely have this guy right there, which is a benzene ring. So I feel like that's going to eliminate this guy, right? And we have a Cl group attached. So that's a chloral. So that is chlorobenzene, 1-chlorobenzene. Do I need a number in this case? I do not, again, because it's mono substituted, there's just 1 there. So that always has to be carbon number 1, which means we really just need to call it chlorobenzene in this case. Yeah. Any questions on that one? Here we have, we really have a toluene, but that's not one of our choices. So we'll go with kind of the older school here. So we still have a a benzene ring there. So that keeps all 3 of these in check. We do have one methyl group and two methyl groups, which is a dimethyl, so that's good, right? So now we need to do some numbering. In this case, it really doesn't matter which methyl you start with. We could go 1, 2, and then 3. So it should be 1, 3 dimethyl benzene. That would also be what positioning? There's the meta positioning. So that also could be meta dimethyl benzene or M dash dimethyl benzene. Any questions on that one there? All right, so aromatic guys has to have the benzene ring. There's a few historical names associated with the benzene ring that you should be aware of. And obviously you also need to know the ortho, meta, and para positioning of the groups and stuff like that. Any questions on that there? All right, that is chapter 11. It is chapter 12 time now, I think officially. There's a bunch of flow charts in case you're into flow charts. I don't know. All right, let's get rid of that. Let's do that. You probably don't want organic. Yeah, we might want organic, I guess. That might be the right one. All right. All right, so in this chapter, it's a bunch more organic groups we're going to officially talk about. We're going to talk about alcohols, which we sort of touched upon a little bit. We're going to talk about thiols, which is sulfur containing groups. We're going to talk about ethers, aldehydes, and ketones. Oh my, let's do it. So alcohols, thiols, ethers, aldehydes, and ketones. So these all have some different functional groups that we're going to talk about. The functional groups really for these guys, alcohols have the OH group. Thiols have a similar one, but it is actually a sulfur containing group. So it has a sulfur instead of an oxygen. Ethers have a carbon, oxygen, carbon sort of run together as their functional group. Aldehydes have actually a carbon oxygen double bond and an H. And ketones have a run of at least 3 carbons in the row, and in that middle carbon is a carbon oxygen double bond. So these are the functional groups of each of these organic guys. We're going to go through each of them individually here in this chapter, and we'll talk about obviously their functional groups and what's going on with each of these here. But basically we're getting into some guys that have obviously some oxygen involved here, a little bit of sulfur with our functional groups. So as we will talk about, these groups are again where most of the activity and sort of action happens with these guys in terms of reactions, and it also affects some of their properties based on what groups that we got going on here. So we're going to start here again looking at our alcohols, phenols, thiols, and ethers, and there's our different groups. So here's our alcohol group. That's our phenol group, which is again really like an alcohol with our benzene ring. There is our carbon, oxygen, carbon arrangement that makes that an ether. That is our thiol group that has our sulfur in there. And depending on what group is present, we do some different ways of naming them. So there'll be some slight changes in terms of how we name them, but most of them will still fall back on those first 10 alkanes that we talked about, and we'll just kind of change some parts of the name as we go through it. So again, our functional groups in line structure, you will still see usually the functional group sort of drawn. So for example, if you had an alcohol like this, you would see the OH, for example, written. As you can see on the bottom there, if you had an SH written, even with, for example, something like an aldehyde, you would see it sort of incorporated into the line structure. And remember, that would be our CH double bonded O. So they do go sort of incorporated into the line structure. And obviously, as you can see there, doesn't look like much, but that is also an ether because again, there's a carbon, oxygen, carbon sort of happening. So we can incorporate our sort of functional groups into our line structure I would say like this. Most of it is going to be kind of drawn out a little bit so you can kind of see it, except for obviously still we don't draw out the carbons that may be involved when you do it. So let's talk about alcohols, and we talked about as we sort of diverged last time into naming alcohols. And alcohols obviously have our functional group of OH, and it ends in OL, an alcohol name. And that is how we basically name alcohols. So we really take the, come back, our longest carbon chain. And again, it does need to have the OH group as part of that longest carbon chain. And we do drop the last part of the alkane name, and we kind of put OL there at the back end of it. So as we maybe saw there, you know, if we had something like this, we would start with our carbons, which is 2. That is going to be based off of ethane. It has an OH group, which makes it an alcohol. So this is known as ethanol. An older way of naming it, as you can see down here, is call it by its group. And that's sort of the common name. And that's why it's sometimes referred to as ethyl alcohol, which is the same as ethanol. And just like methanol, methyl alcohol. So that's the common name. And as I mentioned a number of times, organic molecules, you know, there's the IUPAC way of naming, which is sort of the official way. There's common names, there's historical names, there's something Joe calls it down the street, you know, whatever it may be. There's a lot of names for the same thing. So again, in here, we're going to try to do the IUPAC name on most of it. If it is more of a common name, we might do ethers, maybe more common than IUPAC way. But most of the time, we're going to be shooting for really this sort of naming of our alcohols. Now, as we also kind of alluded to as well, when there is more than one place where you could put the OH group, you do have to give the number of where the OH group is located. So that sort of happens. I just want to draw something. When we get to, again, 3 carbons in the case of alcohols, because we could have something like this. Could also have something like this. So again, in both of these cases, the longest carbon chain is going to be 3, right? That has the OH group also part of it. So they're both going to be propanol. And that obviously is based off of propane, which has 3 carbons. Now, in this case, we do have the OH group right about there. And we do want to, as we've talked about, give the OH group the priority in terms of numbering. So we always want to give it the lowest numbering. So you could probably see that we would want to call that carbon 1, right? Carbon 2 and carbon 3, which means this guy would be 1 propanol in this particular case. While over here, it really doesn't matter which way you go, that OH group is going to end up at carbon number 2 if you went left to right or right to left, and that is what is known as 2-propanol. So in this case, because the OH group has an opportunity to be in 2 different locations, we do need to give the number of where the OH group is located. Once we do that, depending on which way you need to go to number it, you also need to give all the other groups there, right, the appropriate number based on what you chose. Now, we also talked about, I think last time, that you can classify alcohols as well. So for example, this alcohol here would be a primary, secondary, tertiary alcohol. This is a primary because the carbon that has the OH group is directly attached to one other carbon, and this would be a primary alcohol. This guy down here would be, it is a secondary alcohol, as again, the carbon that has the OH group attached to it directly is attached to 1 carbon and 2 carbons. That would be a secondary alcohol. And obviously, if we had something like this, this would be a tertiary alcohol, as the carbon that has the OH groups attached to 1, 2, and 3 carbons would be a tertiary alcohol. So much like how we could classify carbons, I personally, again, think it's easier just to look at the carbons attached to the carbons because it's the same number. Again, sometimes people teach you to look at the hydrogens that there are, but if you look at the carbon to the carbon, it gives you really the number of it is the same as the primary, secondary, tertiary. Speaking of common names, that is 2-propanol, which is technically the IUPAC name. If we condense down this sort of formula, we have something like this. Perhaps you might recognize this group. That is CH3CH3. That is the isopropyl group. And that's why this is also sometimes referred to as isopropyl alcohol, right? Also known as rubbing alcohol as well. All three are the same thing. So this is sometimes also called isopropyl alcohol, more of a common name. Even more common name is rubbing alcohol. So all three of those things is this guy right here. And again, like I said, in organic chemistry, the same thing could have a bunch of different names depending on what you look at. So for us, you should probably roll with 2-propanol, but you should also recognize it as isopropyl alcohol because that is obviously, you might have some in your medicine cabinet, right? So that's obviously used a lot still today and stuff like that. Any questions on classifying alcohols or naming them? Obviously, if we had other groups attached, again, we would want to give those groups an alphabetical order with the appropriate number. So let's take a look at one there. I think we had, right? Yeah, let's do that. All right, so why don't you take a second here. What is the name of this guy? And let me just draw a weird one here. I don't know if it's weird or not, but I'm just gonna rando draw. See how I do. Why don't you also give a name of this one as well? I'll try to figure out what I just drew. All right, let's take a look and see. So once again, we're going to be looking for the longest carbon chain. On the top one here, I think you have two options. You can just go straight across 1, 2, 3, 4, 5, 6. You could also start up here if you like, come down 2, 3, 4, 5, 6 to the right. So you could get 6 if you kind of did that move as well. Since we got sort of the same no matter which way we go, I'm just going to take the kind of straightest way. We also should hopefully see our OH group there, which tells us it's an alcohol. So that is 6 carbons, which is based off of hexane. And it then needs to become hexanol, OL, right? Do I need to give the location of the OH group? I do. And you can probably see that numbering right to left in this case will do the job. 1, 2, 3, 4, 5, 6. Obviously, if we numbered the other way, we're looking at carbon 5 for our OH, which obviously is a larger number. So we always want the smaller. So that's going to be a 2-hexanol for the location of the OH group. And because we sort of locked the numbering in going right to left here, that means that the other group that is there has to be locked into number 5. And that would then be a 5-methyl 2-hexanol. Any questions on that one there? All right, so what I drew here looks like hills. We got 1, 2, 3, 4, 5, 6, and 7 there. That looks like the longest carbon chain there. That obviously contains the OH group as well. So 7 is going to be based off of heptane. And then this will then be heptanol in this case. This way I should number to give the OH group which way, left to right or right to left? Yeah, this way here, 1, 2, 3. Obviously, if you went the other way, bigger than 3, right? 4, 5, 6, and 7. So that's going to be 3 heptanol. That means I locked in my numbering, and my bromine has to be at carbon number 4 in this case. And that's going to give me a 4-bromol 3 heptanol. Any questions on those there? I like the look in the front, like you okay? Sorry. Any questions on that? All right, let's try a couple more here. Let's see. While we're at it, let's do this one to the mix. Why not? Maybe let's do this one to the mix. I like it. Actually, no, I don't like it. I want I like it better now, actually. I really don't like it. Hang on a sec. Not for what I wanted to do. Actually, I'm gonna just get rid of those. Now I like it. All right. Okay, let's take a look. On the first one, you do have 2 options. You go straight across. That looks like a 5-pack. You could also start this way and go that way. We'll get you 5. That's 5 with our methyl group attached there. So that's going to be based off, obviously, a pentane. So that's going to become pentanol in this case. Numbering, so we give that group the smallest number. Looks like a right to left situation here. And that means it's going to be a 2-pentanol along with a 4-methyl. 2-pentanol. Any questions on that one there? That is a benzene ring, right? That has an OH group attached. So that is a phenol, right? That would be carbon 1 because that's where the OH group is attached. Going left here, 2 and 3. So that's a 3-bromol phenol in this case, yeah? All right. Probably a reason why I drew this one, but what is this one here? This is, yeah, so that's cyclohexanol with the OH group, right? So that then becomes cyclohexanol, right? So based off of cyclohexane. In this case, we have a lonely line hanging off of it, which is a methyl group. So a little methyl cyclohexanol. I would say in this case, you probably don't need the 1 because it is technically monosubstituted because the OH is part of what makes it an alcohol. If I laid me up a chlorine there, then you probably should put it the 1 for the methyl, and that would be probably 2, 3 for the chloral in that case. But since that's kind of the only 2 things that would sort of be substituted on there. As the OH, even though it is sort of a group on there, but it's really part of the main part of it, so you wouldn't necessarily need it. Any questions on that? I probably would take it, to be honest with you, but you probably don't actually need it in this particular case. It would be okay. Primary, secondary, tertiary alcohol, this one. This is a secondary, again, looking at that carbon, 1 carbon, 2 carbons. This one, primary, secondary, tertiary. The carbon that we're looking at is right there. It's actually attached to 1 carbon there and 1 carbon there, which means it's a secondary as well. How about over here? Which is really why I drew this thing. It's actually a tertiary one, yeah? And that is because we have a carbon here that we're looking at. That it's a carbon, right? That's a carbon, and that's a carbon, right? Which is really why I drew it. I didn't really care about the name. I really drew it because that's a tertiary carbon right there, right? Our tertiary alcohol in that case, yeah. Any questions on that one there? All right, yeah. I'm sorry, which one? On B, why the OH doesn't need a number? The OH doesn't need a number because that OH is attached to the benzene ring. And that all together is that like historical sort of name that we saw with benzene. That all together with the OH attached to it is the phenol part of it. So that's where it gets incorporated to the name. Kind of similar to over here, even though this OH is sort of attached to it, it gets sort of incorporated over here into the cyclohexanol sort of name part of it. Yeah. Other questions? Okay, we're going to continue on. Any questions so far about naming alcohols? Why don't we draw a couple here just to make sure we still remember how to do it. Let's draw, let's see here. Let's just draw something. Let's do 3-chloral 2-butanol. Let's draw 2-methyl cyclopentanol. And let's do 1 bromol 1 propanol. All right, so draw those up. All right, let's take a look, see how you're doing. So remember, whenever drawing anything, always want to work backwards, right? And just kind of fill in things as you go through it. So we'll start here with the first one here. So I see butanol. So the butane part tells me it is 4 carbons, right? The OL part there tells me it's an alcohol. So that's what I want to start with, is really just the 4 carbons. Again, just like normal, I'm not going to really put anything else but the 4 carbons. That will essentially take care of this part of it. 2 butanol tells me that's the location of the OH group. And since I'm drawing it, I could go left to right, right to left. I'm going to call this my carbon number 1, which means I'm going to put my OH group there on carbon number 2, which pretty much takes care of that part of the name. Because that's going to be my carbon number 2, right next door has to be my carbon number 3 to the right. And that is where we're going to find our chlorine. And just like everything else, it's just going to be hydrogens, right, to fill it in to give carbon 4 bonds. So guy over here at the end needs 3. This one needs 1. We need 1, and we need 3. Any questions on that one? Again, if you're doing a little line structure there, or something like that, and something like that, and maybe something like that. Yeah, we'll look something like that. Any questions on that one? Coming to the second one, again, working backwards, I got a cyclopentanol. So that's based off of cyclopentane, which is basically this, right? It is OL, which tells me it's an alcohol, which means you could choose wherever you like to put that OH group. So I'm just going to put it straight up on top there. Because I put my OH group on top there, that means my carbon number 1 has to be where the OH group ended, right? So if you put your OH on some other carbon, then that would be your carbon number 1 in that case. That's pretty much going to take care of that. The reason that's important is I got to go to carbon number 2, right, and put a methyl. You could go left, you could go right. In this case, it really doesn't matter. So I'm just going to go to the right and put a methyl, and that should be it in that case. Yeah. Any questions on that? Lastly, here we got propanol. So propane is 3 carbons. OL is an alcohol, which is at carbon number 1. So that is where I'm going to put my OH group. I'm going to call that carbon number 1 for me, which takes care of that. By the way, also on that one is a bromine, it looks like, right? And now I am out of things that I need to draw. So we're just going to put in some hydrogens. That needs 3, that needs 2, and really this guy just needs 1 in this case. Yeah, so it looks a bit like that. Any question on how to draw these? So you want to go about drawing them the same way as you draw everything else. Start with just the basic carbons. In this case, figure out where you're going to put your OH group based on the name. And then based on that, everybody else gets put in the proper number location. Yeah.
On the third one, C.
Yeah.
If I had the drawing and I want to name it, do I still have to put the ones?
Would you still have to put the ones you would in this case? And you would need to, because we could have that OH group on carbon number 2, right? And then it wouldn't be 1 propanol at the end, but it would be 2 propanol. So you would have to give that location. Yeah. Other questions? All right, so obviously you need to be able to classify alcohols primary, secondary, tertiary. You need to be able to draw them. You need to be able to give the name and a bunch of other stuff we're going to continue talking about, I suppose. So a little bit about alcohols, ethanol or ethyl alcohol is the alcohol in alcohol, right? So obviously it's made from glucose through some fermentation, and you get your ethanol that is produced there. It is produced by a reactant ethene with water. So as we did with our alkene addition reaction, we could create a alcohol. And that's one way that you can actually prepare an alcohol, is to take an alkene, add water to it, and you will get obviously an alcohol. So that's one way, as we saw in the previous chapter, that you can produce the alcohol. That is where we break our double bond, make it a single bond, H to one, OH to the other. Here's just some other alcohols of phenols. Glycerol is a popular one there in fats and lipids, and it has a lot of OHs. OHs here does allow it to do hydrogen bonding in terms of intermolecular forces, and alcohols with more OH groups can do more hydrogen bonding. Hydrogen bonding, as you might remember, is a relatively strong intermolecular force, and things that have the ability to hydrogen bond typically will have much higher boiling points. So when we look at alcohols, say, versus alcohols versus alkanes, or alkenes, or alkynes, it is the alcohol, bless you, because it has this polar OH group, has the ability to hydrogen bond, and alcohols typically will have much higher boiling points and melting points because of that. As we talked about probably as well, these guys here do not have the ability to hydrogen bond. In order to hydrogen bond, you have to have a hydrogen that's directly attached to a nitrogen, oxygen, or fluorine, and that doesn't happen in those other groups. And because of that, they use dispersion forces, which is those relatively weak intermolecular forces, and they typically have very low melting points and boiling points. So if you have a choice or a question comes about that says which one should have the greater boiling point or melting point, and you have an alcohol in the mix, there's very few things that could be an alcohol. There are some, but there's very few things that could be an alcohol in terms of boiling points, melting points, because of its ability to hydrogen bond. So that's something to keep in mind. That's antifreeze. Antifreeze is an alcohol here. We got two OH groups. If you're not sure what antifreeze does, you put it in your car, and it actually lowers the freezing point, so your car doesn't freeze in really cold weather. And it also does the opposite. It actually increases the boiling point of water, so your car doesn't overheat in really hot temperatures. So it actually does both things and one sort of chemical, which is why we add it to our radiators and that type of stuff to keep it from overheating or really freezing and cold or really hot sort of temperatures. Let's talk about some reactions though for alcohols here. So we obviously saw how we prepare an alcohol, which again is our hydration reaction with our water. Again, preparing our alcohol like ethanol in this particular case. So we could also dehydrate an alcohol, and dehydration is the opposite of putting water on. It's taking water off. So when we have an alcohol and we heat it up, which is sometimes abbreviated with a little triangle for heat, this just means that there's an acid involved as a catalyst, essentially, in this particular case. Not going to really have too much of an effect. But the way we put the alcohol, the way we put the water onto our double bond is also how we take it off. So when we put the water on, right, OH goes to one carbon, H goes to the other carbon. When we take the water off, that's the exact way that it comes off. You got to take an OH off of the carbon that has it, and then the H actually comes off of the carbon next to it, not the same carbon. So we take an H off of there. That is where we're going to get our water basically coming from. When I take the H and the OH, by the way, nothing changes except I take those things out of it. So if I were to draw this, I would copy it exactly the way it's written, except I would take the water out. The problem now between those two carbons is it is short a bond, right? It has only like 6 electrons, right? So just like when we put the water on, we have to take the double bond out. When we take the water out, we got to put the double bond back in. So the double bond basically goes back in between the two carbons where you took out the water in this case. So it's sort of the opposite of putting it on is the dehydration, basically taking the water out. Now, we talked a number of times earlier that when we put the water on, if there is a difference in terms of the number of hydrogens, right, the hydrogen will end up at the one that has the most hydrogens. So, of course, when we have an alcohol, say like, I'm going to try to do this correctly here the first time. We'll hope for the best. Let's see here. Do that. All right, I think maybe I did it right here. Let's see. All right, now we're going to heat this guy up and go to the left there because I have no room going the other way. So we're going to go to the left here and heat it up. I need to get rid of water in this case, right? So we know for sure we got to take out the OH, which is right there. But now we actually have a couple of options as to where we could grab the hydrogen from. We have a carbon to the left that has some hydrogens, right? And we have the carbon to the right that has some hydrogens, right? So there is actually a difference depending on which one you grab as to what you end up with. So the rule when we put the water on, right, if there is a difference, the hydrogen ended up at the most hydrogens. So when there's a difference in the hydrogens on the adjacent carbons, the rule is the opposite. We actually will take the hydrogen from the one with the least. So in this case, we would actually grab a hydrogen off of this carbon because it has the least number of hydrogens. And that means that if I were to draw this, it would look the same. Nothing's going to change except obviously I'm going to take my water out of there. And now where I took the water out, I need to put a double bond there, right, to fix it up. And that would give us our major product. The minor product would be if you grabbed it off of the other side, basically. So if there happens to be a difference and you got like a situation like that where the OH maybe in the middle of two carbons, the one with the least number of hydrogens is where you should take the hydrogen from when you're putting the double bond back in and taking the water out. Now, clearly, if there is no difference and you have, something like this, which looks exactly like what we had before, except that now I'm going to take the OH and both of these carbons have the exact same number of hydrogens, so it doesn't really matter. You can take it from either one in that case. So again, this is only a thing that happens when you have different numbers of hydrogens on adjacent carbons and you need to take a hydrogen from one or the other. You would take it from the least. If there is no difference, then you just take it from whichever one you would like in that particular case. And the dehydration basically works the same always. Everything else stays the same. Take out the water, slap the double bond in between the two carbons. Everything stays the same. Just draw it exactly the way it looks like. Any questions on dehydration reaction? No. Okay. Then let's talk about the oxidation reduction reactions that occur. So in organic chemistry, a lot of times we deal with the other couple of definitions of oxidation and reduction. Oxidation, as we talked about with electrons, means somebody loses electrons. Reduction means somebody gains electrons. Here in organic chemistry, we actually deal with really the kind of two other definitions more often. And the other two definitions for oxidation is somebody gains oxygen as you go from reactants to products. So some element as you go from reactants to products will gain oxygen, and you will lose hydrogen as you go from reactants to products. So those are the two sort of definitions of oxidation that we use. For reduction, somebody will basically lose oxygen as you go from reactants to products, or gain hydrogen as you go from reactants to products. So these are really the two sort of definitions that we sort of look at in organic chemistry when we're dealing with oxidation and reduction, are sort of those two guys. So oxidation and reduction, again, in this situation, does depend on sort of what you're starting with as to what you will get. So as we talked about before, there are primary alcohols, there are secondary alcohols, and there are tertiary alcohols that could go through these type of reactions here. So we have our primary alcohol, which again is attached to one carbon. And again, the carbon that has the OH group is attached to one carbon. And let's take a look at what happens in that situation. So if we take a primary alcohol like this, and I'm just going to draw out everything so we could kind of see here. So we'll take ethanol, for example, which again is a primary alcohol because this carbon that has the OH group is attached to one other carbon directly. So that is a primary alcohol. This will go through an oxidation reaction, which is sometimes just written like an O and some brackets type of thing to tell you that it's going to go through an oxidation reaction. So the oxidation reaction is very similar to what happens when we remove hydrogen, for example, from an alkane, and we put hydrogen onto an alkane. And what happens is the definition here is going to be the loss of hydrogen. So where does the hydrogen come from? The hydrogen always comes from this place, which is one hydrogen will always come from the OH group. So wherever that OH group is, it will lose one hydrogen. And in this particular case, the second hydrogen will come from the carbon that is attached to the OH group. So you could take out either of those hydrogens there. So one hydrogen from each of those locations. When I do that, that is what is going to give me my hydrogen that's going to come off, and basically what's going to cause the oxidation to occur. Now, you may be looking at this and going, what am I left with? Well, you're pretty much left with everything that's not in a box. So you should just copy it exactly the way it looks, which means there's an H, there's a C, there's an H, there's an H, there's a C, there's an O, and there's an H. Yeah. So all I did is copy everything that was there, took out the two box things. Once again, there really should be no excuse why you can't draw anything because it's already almost drawn for you. So all you have to do is copy what is there and just change the small part of it. Now, there is a problem with my picture, right? What's the problem with my picture? Yeah, my carbon is a little short now because I took out the hydrogen. So just like we talked about, when we put in a bond, we have to remove hydrogens, right? So when we remove hydrogens, we got to actually put that bond in. You will always get a double bond that will form between the carbon and the oxygen. So the carbon and the oxygen will always be where the double bond is formed. This creates this functional group here, which is known as an aldehyde. So you go, when you oxidize a primary alcohol from an alcohol to another organic group, which is known as an aldehyde, and that box is what makes it an aldehyde. It's a carbon-oxygen double bond with a hydrogen. Preview time, right? This guy over here is ethanol. The guy on the right, which is an aldehyde, has two carbons, also based off of ethane, except this is known as ethanol, AL, not OL. So that is ethanol right there, which is an aldehyde. Question on that, by the way.
So you take the H from the OH and then which other one?
You always take the second H from the carbon that's attached to the oxygen. It doesn't matter which one you grab. You could grab either one of the, I'll circle it. So you could grab this guy, or you could grab this guy. It doesn't really matter which one you take off, but you just take off one of those guys. And that's from the carbon that is directly attached to the oxygen. Yeah. So always the OH, the hydrogen from the OH goes, and a hydrogen from the carbon is attached to the oxygen, because that's basically where you're going to put your double bond in between the carbon and the oxygen. So just like when we take off the hydrogens and we put the double bond between the two carbons, this is the same idea here. You know, we have something like this. And again, in order to say double bond between that carbon, we got to remove those hydrogens so that we can double bond there. So really, when we look at this part of it, just this part of the alcohol, we're going to remove this guy. So in order to put our double bond in there, we also have to remove one of these hydrogens as well to kind of get them out of the way so we don't have too many bonds. So that is always what you want to think about, is sort of what you end up with or what happens. Always in the primary alcohol oxidation, hydrogen from the OH group, hydrogen from the carbon that's attached to the oxygen, double bond gets inserted between the carbon and the oxygen. Yeah.
And last question, what if the carbon was attached to chlorines instead of hydrogens? So only has the OH and two chlorines.
Wait 5 minutes and we'll talk about it. Okay. We'll get, I think, to your question in just a second. Okay. Other questions on that? All right. So this is actually the oxidation reaction. Let's talk about what happens with our friend, the secondary alcohol. So if we take a secondary alcohol, and we'll just draw something here that's like a secondary type of deal. We'll do that there. All right, so hopefully I drew a secondary alcohol here. I think so. So this carbon that has the OH group, right, is attached to two other carbons directly. So that is going to be a secondary alcohol in this case. Yeah. So again, we're going to do the oxidation here, which means we're going to take out the hydrogen. Just like in the primary alcohol, one hydrogen should come off of what thing? Yeah, so we definitely should come off of there. We also know that the hydrogen, secondly, should come off of the carbon, right? That's attached directly to the oxygen. In this case, do I have options? I don't really have options, right? There is only one hydrogen, so it's got to be that one, right? So once again, now that I box what's coming off, that's going to be my H2. And now I can pretty much copy exactly what's there, except take off the boxes, right? So we'll just draw it exactly, and it should take you like 2 seconds to copy it. And that's probably one situation when you're drawing these things that it might be a good thing not to overthink it, yeah, and just copy what is there so that, you know, you don't hopefully do something weird. The only last thing that I need to do now is lay me up a double bond between always the carbon and the oxygen, right? And there it is, yeah, right there. That, by the way, is our friend, the ketone we just made. And that ketone is 3 carbons in a row that has a carbon-oxygen double bond. That is the functional group right there for a ketone. That is right here. My alcohol name is what did I start with? This, it is 2-propanol. That is a 3-carbon ketone, which is known as propanone, O-N-E, surprisingly. And that is how you name ketones. Ketones end in O-N-E. That's what you put at the end of it. Very creative the way they came up with these things, right? So ketones end in O-N-E. You put O-N-E at the end of the name. There are a few other things that will, when we get there, you have to also take into account, obviously. But in this case, that's what you would end up with. I guess the aldehyde, the Al is different, I guess. So that's a little bit different in terms of that. So if you oxidize a secondary alcohol, you will always hit a ketone. If you oxidize a primary alcohol, like we did in the previous example, you will hit an aldehyde, which is also another organic group. And that brings us to our tertiary alcohol, which we'll draw something like this here, maybe. Actually, now we'll do this here. Do that, do that, do that, do this, do this, do this. Just draw everything out, why not? All right, so I think I might have successfully done that. Let's see. So that's the carbon that's attached to the OH group and it is directly attached to 1, 2, and 3 carbons, right? Which means this is a tertiary alcohol, which I want to oxidize. So again, we're going to remove the hydrogen from the oxygen, right? And now the second hydrogen should come from the carbons directly attached to it. Is there a hydrogen? There is not. That's problematic, which I think was your question. That is a problematic thing. There is no hydrogen there. Yeah. Which means that's a no reaction. So a tertiary alcohol will not be able to go through an oxidation reaction because it's missing that second hydrogen that's needed for the oxidation reaction to take place. So a tertiary alcohol gives you nothing when you oxidize it. It gives you a tertiary alcohol. It will not go through an oxidation, again, because it's missing that hydrogen on that carbon that is necessary for that reaction to take place. Any questions on that there? Yeah. So primary alcohol, if you oxidize it, you get an aldehyde. Secondary alcohol, if you oxidize it, you get a ketone. Tertiary alcohol is the trick question. You get nothing. You get no reaction because it will not go through an oxidation. Again, because it's missing that second hydrogen. Any questions on that there? Now, why we have these, let's talk about going in the other direction, because if you could oxidize something, you could then reduce something, right? And in the case of reduction, it is the opposite reaction. It is basically heading, for example, in this direction. So we'll take a look at the secondary one first, since we got it here. So if we were going in the opposite direction, which means we're going to start with our ketone here. It has our double bond. Reduction heading in this way. We're then going to add H2 to it. What happens in this reaction is pretty much identical to what happens when I have a carbon-carbon double bond and I add H2 to it. What happens to the carbon-carbon double bond? It becomes a single bond, right? And each of them get a hydrogen. The only place we have a double bond in this compound is? Yeah, so that's where this is going to happen. It's going to happen exactly the same way. That double bond is going to become a single bond, and each of those guys get a hydrogen. So let's see what happens here. So you want to kind of draw it the same way as you would what we did previously. So that means I could pretty much copy this identically to what's there, except here we are going to make our guy into a single bond. Everything else going to be the same. It's basically the opposite reaction. And now that I made room, just like we take off the hydrogens, we're going to put on the hydrogens the same way. This guy gets a hydrogen and this guy gets a hydrogen. And now I just went from a ketone to a secondary alcohol through a reduction reaction. And the definition of reduction is it gained H2, right? Which is the opposite way in that case. Any questions on that one? So it's basically the opposite reaction that occurs. Just break that double bond. Each guy gets a hydrogen. Everything else stays exactly the same. Nothing else changes. Question on that? Yeah. Yeah.
Primary alcohol, but has instead of 2 hydrogens, 2 chlores. It will not react. Right?
Yeah, so you need 2 hydrogens to do it, so it won't react because it doesn't have the hydrogens. Yeah. it's a long process of what happens. They just don't pop up, by the way. There's a big thing that's way outside our class in terms of scope of what's happening, but you do functionally need the hydrogen in both those locations for the oxidation to occur. Yeah. Which is why we don't get it when we have that tertiary one, which is kind of a similar situation. If we look at our primary, we could do the same thing with this one because we were able to oxidize it. We could also do the reduction reaction on this one by adding that hydrogen back in. And once again, we would start with our aldehyde in this case. So we'll have our aldehyde here. We will add our hydrogen. And once again, it is this double bond that we're just going to make into a single bond. So we're going to copy it exactly the same way, going in the opposite direction. And double bond becomes single bond. And now we have a place for both of our hydrogens to come in. We'll pop a hydrogen onto our oxygen, pop one onto here. And now we have our primary alcohol back and our aldehyde that we started with. So obviously you can oxidize a primary alcohol to an aldehyde. And if you change your mind and want to send it back the other way, throw the hydrogen back on and you can reduce it back to your alcohol. And same thing with your secondary alcohol. You could oxidize it to a ketone. And if you want to throw it back the other way, throw your hydrogen back in the mix and it will go back the other way. Tertiary alcohol ain't going anywhere. It's not going to oxidize. And obviously, if you can't oxidize it, you can't send it back the other way. It's just going to stay that way because of the lack of the hydrogen. Any questions on any of the alcohol type of reactions? What's going on? Naming? I think that's most of them there. Yeah. All right. I think it might be a good place to lay it up there.